we've been talking about minimizing this expected loss. So we want to get a small loss on average when we're thinking about decision theory. And we had these two cases, one where we are given x, so we're minimizing the conditional expectation, and the more general case where we want to choose some f for all x's. And we found that we could, if we could solve the first problem, then we could solve the second problem because it decoupled into just a bunch of a bunch of individual cases of the first problem. And that was very nice. So we found that it did not depend on this marginal distribution, the solution. This was not a key quantity in that solution. And now I'd like to take a look at how this plays out in the case of the square loss. We looked at the 0,1 loss, and now we'll think about the square loss. And the square loss is used for regression. So the square loss we defined in another video, and that's just the square of the difference between our prediction and the true value. And for this, we're again going to have random variables x and y, but now y will be there will be a PDF. Y will have a density, because for regression we want to have continuous valued y's, we want to have real valued y's. So classification, so having a PDF wouldn't really make sense here. Well, let's write it. Let's still write it as p just to keep things simple. So p is going to be some density. And let's think about the conditional expectation. So we'll think about case 1 where we're given some x. And let's write down what this conditional expectation looks like. So we've got the loss, y with y hat, and condition on some particular value of x. So what is this? Well, we know from the rules of expectation we can write this as the integral, since this is a density, it's the integral of the loss times the conditional density of y given that x equals this little value of x. And this is integrating over all values of y. So it's an integral from minus infinity to infinity, or whatever the range of y is. So y is real valued, so it would be minus infinity to infinity. And this is a density. So let's plug in our definition for the loss, and let's see what happens when we try to minimize this thing. Oh, the square. Let's suppose, we want to minimize this. So to make our life easy, let's suppose this is a very nice, smooth function, because we're going to want to take derivatives and stuff. So let's suppose this is smooth in the sense that it has a continuous derivative. Smooth enough so it's nice enough so that we can do the following. In calculus, when we want to minimize something, the standard trick is you differentiate, you set the derivative equal to 0. And here we want to minimize with respect to y hat. So we're going to differentiate this thing. Write that. Differentiate this with respect to y hat. And what is that? So we're making this assumption, this smoothness assumption, so that we can do the trick of integrating under the integral, or differentiating, I should say, under the integral sign. And this just, we just assume this is smooth enough, that it's nice enough that that this is justifiable. So we can move the integral under. I'll just write it here. dy. And what is that? Well, we just do our calculus. Let's switch these so we don't get a negative sign. We can always switch these since the square cancels the negative. So this is 2 times y hat minus y. Right, the 2 comes down. Differentiate that, and it's 1. P of y given x. It doesn't depend on y hat, so we're good. And now what happens? Let's rewrite, well, let's expand this out. So we've got y hat's a constant, so we can pull it out, minus 2 times y, p of y given x, dy. And now, what do we have? Well, so things are looking good here. This is just, well, so right, this is a conditional probability distribution, and we're integrating over all possible values of y. So this just integrates to 1. And this is the definition of the expectation, or rather the conditional expectation of y given x. So this is the expected value of y given that x equals little x. So this is looking nice. And now we've set this equal to 0. So let's, well, we can just divide by 2 and nothing changes over here. And we solve for y hat. So this implies, if we set it equal to 0, that y hat equals the conditional expectation of y given that x equals little x. So this is a critical point, at least. It's the only critical point of this function as a function of y hat. From our calculus, we know it's a critical point. And to verify that it's a minimum, let's see, so we need to take the second derivative, and if the second derivative is positive, then it's a minimum. So let's see, if we took the second derivative here, so we would have taken the second derivative of this part, and y hat doesn't appear anywhere over here, so that's a constant, goes to 0. And the derivative of this is just, well, it would be 2, before we cancel the 2. It would be 2, which is strictly positive, and therefore this is a minimum. So this is our solution. So that implies that e of y, the expected value of y given x equals little x, is the solution to this minimization problem, minimizing the expected value, or the expected loss, given x equals little x. So that's a beautiful little result. In the case of square loss, when we take the square loss, then this conditional, minimizing this conditional expected loss, turns into just solving this conditional expectation. So that's a beautiful result. So square loss, oftentimes people will use the square loss because it has these very nice properties, and this is one of the properties that the square loss has, and which makes it very nice to use. And it's also, this has a very intuitive interpretation. So let's think about what is this saying? Let's think about an example here. Let's draw, just say maybe just some 1D example. Say this is x and this is y. And we've got some points. Well, let's say we condition on a particular value of x, right? That's the situation we're thinking about for now. And there's some conditional distribution, some conditional density on y. So let's maybe I'll just draw that as though we were sampling from this conditional distribution. So we had, whoop, not that one. It's got to be there. So maybe we got this distribution. Maybe this distribution looks like this. So it's more dense here, and it's smaller out here. Well, what does this solution say? We're doing regression, remember, so we have to predict some value. We have to choose some function, f of x, and this says you should choose f of x, your y hat, for this x to be the expected value of this conditional distribution. That's what this is. This is the expected value of the distribution of y given x, the conditional density. And that's just a very natural thing to do, right? You take the average sort of value. So we were thinking about solving this for a particular x, but if you remember when we were considering that, so that was case 1, but case 2 we had to define a function for all x's. And it turns out what we found was we just solved for each individual x, and by solving that minimization for each individual x, that gives us the minimizer for all x's. So we immediately have that the solution to the minimization problem for the square loss for regression is to take f of x equal to the conditional expectation of y given that x equals x. Beautiful result.